Okay, good evening, everyone. So today we want to be looking at ANOVA. And ANOVA is acronym, yes, for analysis of variance. So if you remember, for those of you who have been around, you remember when we talk about the different ways the different type of hypothesis tests. We also talk about whether they are, we talk about whether they are parametric or not parametric and the purpose, what they are for. So for compare, if you remember when you compare two means, which means you are talking of association between categorical variable and a quantitative variable. But the category, that categorical variable has only two categories. That is, we are comparing two means. We use t-test. But when you compare more than two means, that in the situation, yes, association between categorical variable and quantitative variable. But the category of that categorical variable is more than two. Maybe three, maybe four, maybe five. We cannot use mean to compare. We use ANOVA. I want to look at the rationale behind that. So we look at the rationale behind that. Okay, anyway, I don't need to repeat myself about these are the formula for the student t-test, peer t-test. Let's look at ANOVA. ANOVA means analysis of variance. ANOVA is a group of statistical methods employed to compare the means of three or more groups. It is good to understand that t-tests are not used to compare means of more than two groups. Therefore, it is good to have an understanding of the concept of family-wise error. It's because of the concept of family-wise error that you cannot use t-test to compare more than two groups. So look at it. So we see something, if you apply this combination formula, where you see number of possible combination of the group. So you see how if you have arrow unit of item, maybe you have children A, B, C, and you want to compare them. N is the number of items. Unit of combination is the pair, that is unit means 2, 2. R will be 2, N is equal to the number. If the number is 3 now, 3 item, 4 item. But that arrow is, you know that is the unit of combination. When you say it's 2, that's you are pairing. So C is not the number of possible combination of the group. So you say C is equal to n factorial over n minus r factorial, r factorial. So if you say, look at it now, K is if the number of group to be pair is K. You can use the word K. Normal, in mathematics, they use the word, the one we just saw above, but when we try to talk about it here, they change the pattern. So if they just replace the n with K, combination is K factorial over 2 into, because you want to pair it, into K minus 2 factorial. Now, if you remember, we say it's pair, we want to pair, R is equal to 2. In that situation now, you can't see the R, we have put R there. The R, you say R is equal to 2. R factorial is still 2, because 2, if the meaning of factorial is 2 times 1. If you say 3 factorial, I mean 3 times 2 times 1. If you say 10 factorial, I mean 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 factorial. So when you say 2 factorial, hard factorial, since our R is equal to 2, it's already 2. It's 2 times 1. So that was going to say, okay, K minus 2 factorial. So the family-wise errors that would now say, okay, 1 minus 0.95 C. C, number of tests you carry out. The combination. So now, I think there's this table here before I come back to that one. So all this I just look at it here. If you calculate that for number of pair, if there are only 2, the first one, a number of group 2 group, that's what you use for that's the main for you, the t-test, where you have only 2 group. You can only combine 2 pair 2 group in only one way. That's we see number of pair, that middle column is 1. But if there are 3 now, it give you 3. So if the number of pair, there are 3 group, maybe you have intervention A, intervention B, and control, make it 3 group. In how many ways can you combine them? Can we pair them? It's 3 ways. 3 factorial over 3 minus 2 factorial times 2 factorial. When you solve it, it will give you 3. If there are 4, look at it, it's very simple. If you are A and B, you can call it, there are 2, A and B group. That's only way, one way, A and B. If it's 3, A and B and C, it's 3 way, A and B, A and C, B and C. Can you see now? 3 way. If there are 4, there are 6 different ways. You say you have A, B, C, D. You're going to say A and B, A and C, A and D, B and C, B and D, then C and D. If you combine like that, it gives you 6. If there are 5 groups, you can pair them in 10 different ways. As it's going, can you see it going like that? But we'll be using an example, this simplest one, which is 3 group. Now, look at the last 2 columns. Okay, before that one, let me go back to that. Look at this. What we just mean here is that if when you carry out your hypothesis test, it turned out a p-value, and instead of level of significance most of the time to be 0.05, which is 5%. That's the probability of committing type 1 error. Your probability of not committing type 1 error will be 0.95. Can you see now? Because if your probability of committing type 1 error, that is the p-value, is 0.05, that's probability of saying that the difference is due to chance, that is 0.05. The probability that the difference is not due to chance will be 1 minus that, which is 0.95. Now, if you come here, if you do the test once, if it is only 1 test, like that first example in the first row now, which is for t-test, 2 group, your level of significance is 0.05. That's why it's 5%. But if it is 2 group, 3 group rather, you are going to do 3 tests. Each of them is 0.05. So if the level of if you have set your level of significance to be 0.05, the probability of not committing type 1 error will be 0.95. So, but if you now do 3 group now, what will happen is that it will increase your this thing to 14.3%. Let me see if there's anything that I think that That's the demonstration anyway. So 40.3%. What it means that when you multiply 0.95 times 0.95 times and now remove it from 1, it will give you 0.4143, which is 40.3%. If there are four groups, that means you are carrying out 6 tests. That is 0.95 times 0.95 times in 6 occasions. Remove it from 1, it will give you 0.265. That's 26.5%. Can you see the way it's increasing? So that shows that when you carry out 3 hypothesis tests at the same time on an issue, your level of the probability of committing type 1 error is not just 0.05. Level of sigma is not just, has increased to 40.3%. So there is 40.3% of you committing type 1 error. If it is 6 tests you did at the same time, it has increased to 26.5%. If it is 10 tests you did, 40.1%. Can you see now? As the number of group and the number of pair increases, your probability of committing type 1 error increases. That's what we call family-wise error. That is error we call a family of tests. When it's a family of 10, it's not only one test. 2, 3, 4, 5, 6. So when the test, like for example, now the first one possible is 1, the other one is 3, the other one is 6, 10, 15, 21, 28, 13, 36, 45. Look at 45, the last one, when you have 10 groups, you pair them in 45 ways. So if you do tests for all 45 tests, your probability of committing type 1 error has increased to 90.1%. Which is dangerous. So because of this logic, the intelligent people now say, well, it's not possible. It doesn't make sense. They now came out with this idea of ANOVA. This ANOVA is also called health test. It tells us whether 3 or more means are the same. It produces F statistic. The statistic is F, which is similar to the T statistic in that it compares the amount of systematic variance in the data to the amount of unsystematic variance. You know, I already told you the systematic variance is the numerator. That is the amount of difference you study, you want to find out. Whereas the unsystematic, which is represented by the standard error most of the time, is the denominator. So it's at least similar to theta in that sense, but the issue is the way it's carried out. F is the ratio of model to error. We'll talk about that. It's the same thing. The model is the numerator. It's the study you that now want to do experimental design. You have about 3 groups. You want to find, is there any difference? So the model is the difference between the 2 groups, the 3 groups we are looking for. Why the error is the inherent variability within the 3 groups, which is the denominator. It is also called F10 to reflect the name of the person that developed the technique, which is Fisher. Fisher, look at it. Sarona Fisher, regarded probably as the wisest man ever, cleverest person ever. Probably clever. So this man was the one that before the computer came, that generated statistical table. All the statistical table we use, the one that generated them, was a geneticist. Those are the pioneers in the development of statistics. Then the theory of ANOVA now. The ANOVA, as I've said, examine the variation across all groups at once using concept of variation between group, variation within. So how does it do it? Look at variation between group, variation within groups. The variation between group is the numerator. That's the one that is looking at the system, the model, variation between groups. While variation within group is the error, is the denominator. If there's no difference between the group, then the ratio of the variance between the group and within the group should be 1, since the variation will be the same. So if there's no variation, that shows that numerator will be equal to denominator. So variation between group divided by variation within group is 1. In that situation, there is no difference among the groups. If the group differ, so variation between group divided by variation within group will be less than, will be greater than 1, not less than, greater than 1. So ANOVA is an omnibus test. What it means that omnibus means that it tests for an overall effect, or if there's or are any difference among the all groups. So the issue is that you are looking at, is there any difference anywhere among the groups? You know, it's more than 2 groups, either 3 or 4 or 5. But it will not tell you where the difference lies. It's an omnibus test. Test the overall difference anywhere that can be found anywhere. However, it does not provide information about where the difference lies. Assuming 3 means are being compared, every ratio may tell us that the mean are not equal. You may say that the means are not equal. However, there are several ways in which the means can differ. It can be all the 3 means are significantly different. That is, S bar S1 by S2 by S3, all of them, they are not the same. It may mean that 1 or 2 are the same, but the other 3 different. By S1 by S2 is equal to by S2, but not equal to by S3. It may mean that 2 or 3 are the same, but one are significantly different mean. That is, by S1 is not equal to by S2, but it's equal to by S3. It may mean that 1 or 3 are the same. So the difference can be found anywhere. So what is now there is that it is after you find the difference. If you can find the difference, we may now, if you cannot find difference, that shows that difference does not lie anywhere. But if you can find difference, it does not end it. You have to now use other things to find out where the difference is. So, but what you do is to first of all find out, is there any difference anywhere or not? I'm sure this will look like as if you are speaking Latin. But now, you understand it better when we use an example. This is an example. We have libido score of 3 groups of participants with different intervention. Yeah, you know what the libido, to measure libido. So 3 different interventions. One is group 1, you give placebo. You don't give anything to enhance the man's libido. Just give something that is shock. Group 2, you give Viagra, low dose Viagra. Group 3, you give high dose Viagra. And in each group, there are 5 people you can see. So maybe you will now put the thing on a scale of 1 to 10. After the performance, you ask each person to rate. How did you rate your libido on a scale of 1 to 10? Look at what the result gives. For placebo, 3, 2, 1, 1, 4. Those are the 5 people. There are different groups. It's not just the same person. So we have 5 groups that were given placebo. So 5 groups are given low dose, and they have this 5, 2, 4, 2, 3. While the other 5 group, 5 people rather participants, the other group, high dose. So this is their score: 7, 4, 5, 3, 6, 5. You will see their mean score in 6 rather not 4. So you see their mean score by X. For the group 1 is 2.2, for the group 2 is 3.2, for the group 3 is 5. You also see their standard deviation. For group 1 is 1.3, for group 2 it's 1.3, for group 3 is 1.58. And you can see their variance also. So group 1, 1.7, group 2, 1.7, group 3, 2.5. Now, you will see something calculated under also. Grand mean, 3.467. Grand standard deviation, 1.767. Grand variance, 3.124. There's something that I want you to notice here is that each of the group has their mean value. But you now have grand mean. Each of the group has their mean standard deviation and whatever. That is their mean and variability. That grand mean is the combined collapse all the 5 together, all the 3 groups together, all the 15 participants. The grand mean will be the mean and with the standard deviation. Another way of calculating that grand mean, you may not calculate for all the 50 together. You may not calculate the mean of the 3 means, 2.2 plus 3.2 plus 5 divided by 3, still give you this grand mean. Does it make sense? So you understanding this one will help you to understand the variability we are talking about. If you remember when you tried to calculate the mean, you want to calculate standard deviation and variance. You remember what you do? You remove the mean from the each value. You remove mean from each value. It gives you the deviation. You now square it because we already know that deviation from the mean, some will be negative, some will be positive, some will be 0. If you try to add it together, it gives you 0. Because as many that are less than the mean are also more than the mean. Because the mean is the middle value. As many that are less than the mean, lower than also higher than the mean. So when you are trying to remove mean from each value, those ones that are less than the mean will give you negative value. Those ones that are the same with the mean will give 0. Those ones that are higher than the mean will give you positive when you remove mean from it. So you're going to have a range of value from negative to positive. If you have to try to add it together, it gives you 0. So that's why intelligent people now square it. They know that when you square something negative, everything becomes positive. So when you square it, it's not the way we calculate our variance. You see, we call it square deviation from the mean. Square, I've already explained it for square deviation from the mean. So that's what we have just done. We are doing on this table, you see. So let's arrange them. The first column is to arrange them 1 to 15, the participant. The second column is to put the group. So the number 1 to 5 is group 1. Those 5 people in group 1. Number 5 to 10 is the 5 people in group 2. Number 11 to 15 is 5 people in group 3. Third column is the mean, is the value. That is the libido of each person. Now, if we want to, the first thing we want to do for each of the value within each group, we want to remove the mean of each group from each value. So you see now, for number 1 to 5 now, the mean of each group, of that group is 2.2. We remove it from 3, 2, 1, 1, 4. That's what gives us what you have there. Then from number 6 to 10, the mean from their own group is 3.2. We remove it from those values 5, 2, 4, 2, 3. That's what gives you those values you see under X1 or X bar, that fourth column. Then for group 3, from number 11 to 15, the mean of the group is 5. You remove it from those values there, which is 7, 4, 5, 3, 6. Give you this value. Of course, if you're trying to add it together, it will be 0. So if you square the value, that's what we call sum of square within the group. Sum of square within the group. If you look at it, we did it for by removing the mean of each group from the group value, sum or square within the group. Now, the second, that is the sixth column now, that has bar x minus double bar x. What it mean? No, I already told you also that you can calculate what this one is looking at now. That gram mean, which is total mean for all of them, if you remove it from each of the three means, you remove it from each of the three means, it will give you by x minus by double x, double by x. So look at it now. Look at that minus 1.27. You see from 1 to 5 the same, because the group mean is the same for the group now. It's group mean 2.2. So if you remove gram mean, which is 3 point, that is slack there. The gram mean, which is 3 point something. If you remove it, yes, 3.47. Yes, sorry, 3.47, which is the gram mean. If you remove it from that 2.2, it gives you minus 1.27. So because number 1 to 5 is the same group, 1, that's why you see it's the same value. So if you remove this gram mean 3.47 from mean of group 2, which is 3.2, it gives you minus 0.27. Since number 6 to 10 are in the same group, that's why you see the same value. Then the last one, you remove the 3.47, the gram mean, from 5, which is the mean of group 3, it gives you 1.53. That's for all the ones in that group. So now you have negative, positive. If you add together, it gives 0. You square it. When you square it, which is the next column, it gives you, we call this one, you now add it together, I call it sum of square between. So it tries to give you the variability between group. So the first one, x minus by x square, which give you, add together, give you 23.6. That is sum of square within groups. This one is sum of square between groups. So the last one now, you see the last two columns. Second to the last column, you see x minus double by x. That is, you remove gram mean from each value. See, you combine the 15 together, remove the gram mean from each value. So each value, this value, the way we have arranged it from 1 to 15, each value 3, 2, 1, 1, 4, that's each value in column 3. 3, 2, 1, 1, 4, 5, 2, 4, 2, 3, 7, 4, 5, 3, 6. When you remove the gram mean from each of them, it gives you this, that second to the last column. When you square it, it gives you total sum of square. So now, if you had 23.6 with 20.1335, it will give you 43.7335. So what is telling you now? The first one, sum of square within, tell you the variability within each group. That is the inherent variability. But the second one, sum of square between, that is the variability between group. That is the systematic one you are looking for. This last one is just the total variability. So that is total variability. That's why we say ANOVA, analysis of variance. Variance is a measure of variability. So total variability is what you get with this last one, sum of square total variability. That total variability is divided into two: variability within group and variability between group. So when you see you see groups of data. Although it's the same thing applicable to even two group as by the way you use it as or it's only that you can just use it. So when you have means you see data sets, 3 group, 4 group, the variability in the data set is divided into 2. Yes, the total, you can call the total variability. Then it's divided into 2. Variability within each group and variability between the groups. Variability within group and variability between group. It gives you the total variability. Now, if you want to calculate the variance now from the sum of square, let's see, MSB, mean square between, mean square, MS means mean square. You know, mean square is the variance. You remember the way you calculate variance now? You say sum of square over the standard error, n minus 1. So that first one you see here now, MSB, mean square between. So the variability between, which is 20.1335, over the standard degree of freedom, rather, which is 2. Why? Because there are 3 groups. So 3 minus 1, that's why the degree of freedom is 2. So the mean between the mean square, that is variance between the group, 10.067. The MSW means mean square within, mean square within the group. If you remember, the total, the sum of square within is 23.6 over 12. You remember that each of the group is 5, 5, 5. So each of them, the degree of freedom will be, for group 1 will be 5 minus 1, which is 4. For group 2, 5 minus 1, which is 4. For group 3, 5 minus 1, which is 4. 4, 4, 4. Adding together give you 12. That's why the degree of freedom within is 12. So when you now calculate the mean, I give you 1.96. So what this one is telling you is that the variability, the variance between the groups is 10.067, but the variance within the group is 1.96. So now our test statistic is variance between divided by variance within. It is when the variance between is far, far, far bigger than the variance within that we say is significant. So F now is mean square between over mean square within. You go to 10.067 over 1.967. It gives you 5.119. This is the F. Of course, you need to go and check table of statistic table for you to get. With computer, when we run it now, it will give you the p-value. Any question before we go run it? We continue discussion. Any question? Ask question. This is where to conceptualize it. Once you can get it, there's no big hearing of analysis of it. There's nothing big there. There's no big deal there. That's what I'm just telling you. I just explained now. Any question? Nobody? You are 4. Mila, Dr. Mila, no question. Farouk?
No question, sir.
No, sir.
What of a neighbor? And then, boy, are you out? Okay, let's continue. So, I want to run it. Farouk, are you ready to share? Well, you are the only one. Otherwise, I will share from here. You are the only one.
No, sir.
You will come late. The day this, I don't give this lecture, and you don't come at all, is the day the lecture ends. So there's no point posting what does not, as if it's me that is begging people to. It's you people that say you want something and I give it out freely. The people, I don't know. So I think the low dose diagram, this particular data now. So if you are to do what you need to do is that data must be entered in two columns. That is the dose, which is the group, whether placebo, low dose, or high dose. Then the libido, which is the quantitative variable, the libido score. So when you code it now, say, you can put 1 placebo, 2 low dose, 3 high dose. So the step involved. Let me share my. Let me share the SPSF because I've already. So you can see it. You can see the way I enter it. Forget about those dummy. They are for something else. If for something I can, well, it is when we do regression, I can demonstrate it. Because the reason for putting it there is to demonstrate to you that regression and ANOVA is the same. Regression method and ANOVA is the same. In those days, the researchers that were interested in experimental research, they used ANOVA a lot. While those ones that were doing observational research use regression. Because, in experimental research, you're able to control for confounder at the design stage. That's why you have those different groups when you do your selection. And you have those different groups. You are able to control for a lot of confounder at the design stage. For observational research, because you cannot control for a lot of confounder at the design stage, it's during analysis you now control. You now use regression to control. But it's virtually the same. So the first two columns is what I just explained the other time. Dose, that is those, the dosage. Those, the first 5, they are group 1. So the value is just the group is the way I label it. So if I come to click on this value label, you see that the first 5 is placebo, the next 5 is low dose, the remaining 5 is high dose. And libido score is the score we are interested in. That is the score itself. So if you want to do the analysis, you now say analyze, compare means, you will see under it one way ANOVA. So dependent list is the libido. The factor is the dose. You move it here. So here, if we won't touch anything, you just say, okay, let's just bring the result. I guess you can see this. Can you see the output? Or share, reshare? Can you see the output? If you are talking, you have to unmute. Otherwise, I'll not hear you. Can you see the output? Somebody should talk now. Unmute and talk. If you are talking, you didn't unmute, I will not hear you.
No, sir, we can't.
And I have to reshare. Can you see now?
Yes, sir.
Yes. Look at the output. Look at it too. Look at the first column. That's the way I say between group, within group, total. Hmm? You know, everything about ANOVA is between group, within group, and the total. Let's look at the sum of square. Look at the sum, that is when you remove mean from a value and square it. Look at between group, 20.11133. That's what we calculated the other time. Within group is 23.6. The total is 43.733. Remember the total, we got it by removing the grand mean from each value or each of the 15 value and now square the difference to get this. And whereas the between group, we got it by removing each class mean from each value. For all of them like that, for the three group like that in a row like that, and now square. While within group, what we did was to remove the grand mean from each of the three group mean and square. So we see that if you had between group plus within group sum of square, it gives you the grand total in total. Look at the degree of freedom. We did the other time between group, because there are three group. 3 minus 1, that's why it's 2. Look at within group, degree of freedom. I've already explained. You know, each of the group is 5, 5, 5. 5 minus 1, 5 minus 1, 5 minus 1, making 4 plus 4 plus 4. It gives you 12. While the total degree of freedom is the total, all of them is 15. 15 minus 1, 14. And if you had the 2 plus 12, it gives you 14. Mean square. Mean square is by dividing the sum of square by that degree of freedom. So 20.133 divided by 2, it gives you 10.067. 23.6 divided by 12, it gives you 1.967. 43.733 divided by 14. Okay, this one, we don't need it. That one doesn't, it's not needed. That's why. Then F test is mean square between group divided by mean square within group, which is 10.0767 divided by 1.967. It gives you 5.119. That is the F. That is the ANOVA statistic. And the corresponding p-value is 0.05, which is significant. Any question? Any question?
No, sir.
So simple. Now, you know, I told you before, if let's say after we have done this one now, it's not significant. You go and rest. That's you, that there's no difference anywhere among the group. You rest the case. But now that is significant, where does the significant lie? So let's go back to our slide. Okay, this one is just showing my there's something where I put this is advanced this okay, don't worry. Okay, I think put okay, it's explanation. Now, so what we now do, did I change that slide? Okay, before we move further to do that, let me just explain this slide for you, what we're just finished doing now. If they ask you formula for ANOVA now, it look complex, but if you understand, you can even write it. I say sigma x bar minus s double bar square over j minus 1, everything all over sigma s minus x bar square over sigma n minus 1. These two lines, the first line, you put it over the two lines. Imagine somebody wrote that type of equation. What does that mean? Very simple. The first one, what does it mean? Sigma just means the x minus s bar minus double s bar that you did before, group mean minus ground mean square over number of group minus 1. J is number of group minus 1. That's why if you look at it now, this one over 20 over 2, 20.1133 over 2, that now give us 10 point this. And the other one, that means this first one is mean square between, mean square within sigma, that is s minus s bar for all the group, s minus s bar square over sigma n minus 1. You remember that each of them, n minus 1, 5 minus 1, 5 minus 1, you add it together, sigma n minus 1. This is 12. So when you now put this 10.067 over 1.967, it gives you 5.119, which is the. So imagine now you now put this first formula over the second formula, say ANOVA. That's it. There's no big deal there. That's the explanation. So let me, there's some of these reasons for this is not here. Let me just stop sharing and share back the expresses. Or let me share back the data editor window. Now that we have seen that there's a difference somewhere, maybe in all between all the group, we don't know where the difference lies. Is it between low placebo and low dose, or between low dose and high dose, or between placebo and high dose? We don't know. Now, what you now do, there are what we now do it, we call it post hoc test. In the post hoc test now, you want to do as if you want to do t-test. You combine them in 3 places, but the way they have adjusted for it, they have adjusted in such a way that you will not have that family-wise error. The type of p-value you're going to get, you will not have that family-wise error. So you're going to run the test, compare low dose and placebo and low dose, placebo and high dose, low dose and high dose. Those 3 different combinations. We call them post hoc tests. So let me just go. I will show you those post hoc tests in the expresses. You go back to that. Compare means one way ANOVA. Now, hope you can see. So we now come to this option, post hoc test. And you see the different post hoc test that the option that this thing give us. The different option. We have LSD, Bonferroni, Cedar, Sheffield. So the first setup, they call the equal variance assume. The other one, equal variance not assume. Maybe before we move further, just wait. Let me stop sharing. Let me share, because I was not seeing, but I think it's there in the event. You mean that it's not patient enough? It should be on my side. I cannot leave my slide. The explanation. This was just where I talk about probability F. There's no time to be talking about that edge distribution, whatever, and the F table. So one of the, if let's say we cannot find the difference, we can use either Planck constant contrast or look at what I was trying to this. F ratio tells us only whether the model fitted to the model account for more variation than extraneous factor. But it does not tell us where the difference between those groups lie. There are two ways to contrast the different group without inflating the type 1 error rate. The first one is Planck contrast. That is Planck comparison. You break the variance accounted for by model into component parts. That's Planck contrast. Then post hoc test, comparing every group using a strict acceptance criterion so that the family-wise error rate does not rise. That's what we are going to run. The Planck contrast, we can use it, but the one that is being used most of the time is post hoc test. This is Planck contrast. I will not discuss Planck contrast, but let's just go to that post hoc test. Because that one is a lot of gimmick. I think we are in post hoc. Yeah. So this one just giving the group what I wanted to go and do. So I think we can go and do it now. But look at the post hoc test. Those ones that I'm showing you, look at it. The different post hoc tests you can carry out. These first 14 equal variance assume, that is, if you assume that there's homogeneity of variance. You know, one of the ANOVA is a parametric test. One of the requirements, apart from normally distributed data, is it must have homogeneity of variance. There's no heterogeneous. Homogeneity of variance, second most important condition. So here, if you assume that, oh, they have equal variance, those 14, they are the best. But if you cannot assume, then these 4 come into play. So let me go and run it now. With all those explanations, we see it, they are there. All those other things. Well, when I was. So this is where we were. So what I did, so let's choose LSD, Onferoni, and Games OL. That's what I usually do. Look at it. We just want to use, it's the same thing. All those 3, they are doing the same thing. I just, out of the 18 example they listed here, let's just, it's even more than 18 now. All these examples they listed here, let's just choose these 3. I will explain. So let me share the output. So if you let's look at just LSD first. You just arrange all it's the same thing. LSD, but it gives you different, because it's different method. Different, it's the same method, but different people that invented those things. So that's why you see the variation in the value, but it's virtually the same. Let's look at that LSD. You see what it does is that it pick placebo and compare with low dose, and placebo compare with high dose. Can you see now? And now pick low dose compare with placebo and low dose compare with high dose. You now pick high dose compare with placebo and high dose compare with low dose. By doing this, it's only 3 combinations we need, but we have 6 combinations here because there will be repetition. For example, now you just need placebo stroke low dose is the same thing as low dose placebo. A and plus B is the same thing as B plus A. Placebo high dose is the same thing as high dose placebo. Low dose high dose is the same thing as high dose low dose. That is why you will see, what can I see there for you? Okay, let me first of all explain J. Remember, J is the group. So the difference between each group now, you remember that the low dose placebo, the mean for the group is 2.2. For the low dose, the mean is 3.2. The difference is 1. That's why, can you see now? 1. Placebo stroke low dose. The J minus this, that is the mean difference. Can you see now? It's 1. It's the same if you come here, low dose and placebo. We have already said that placebo, low dose, it's the same thing, 1. The only one, the one will be negative, one will be positive. Because this first one, you remove 3.2 from 2.2, it will give you negative now. But here, you remove 2.2 from 3.2, it gives you 1. Can you see that? So you remove bigger from smaller, it gives you minus. You remove the smaller from the bigger, it gives you positive, but it's still the same thing. So the same thing when you now come to placebo and high dose. Remember, the mean for placebo is 2.2, high dose is 5. When you remove 2.2 from 5, it gives you 2.8 rather. That's why you are seeing this one. It's the same thing here. High dose placebo, 2.8. It's just negative, positive, minus, plus. It's just different direction. The same thing with low dose, high dose. Low dose is 3.2, high dose is 5. So when you remove 3.2 from 5, it gives you 1.8. The same thing here, high dose, low dose. So can you see now? So if you go to either benfluorenin again, it's the same thing. Let's now look at the level of significance. Let's look at the significance, which is the p-value. You see, the difference between placebo and low dose is 0.282. That's p-value. It's the same thing you see here. Low dose and placebo is the same thing because it's the same thing. I compare in different way. But the difference between the association between placebo and high dose is 0.08. And the same thing saying high dose and placebo, 0.08. If it is between low dose and high dose, is 0.65. The same thing I say high dose and low dose, 0.65. So it's actually 3, but computer is not human being. So for you to get the result, the 3 combination, you have to arrange it like this. So man is still superior to computer. So because computer will not think whatever program, and that's the only way you can do that. That's why they do it like that. It's just for you to understand and bring out your result. Now we have explained that. Now let's now look at that. The one, if you look at it, the only significant that is less than 0.05 there is the association between low placebo and high dose. That's one that is significant. What it's telling you is that there's a significant difference in the libido between somebody that did not take the Viagra and the person that take it high dose. So if you look at between placebo and low dose, there's no significant difference. It means that if the person that just take low dose, it's as if the person that's not taking anything. It doesn't affect the performance much. And also, you see that the low dose and high dose between the 0.065, almost significant. That is, somebody that takes high dose and somebody that take low dose. But if you look at games, oh well, let me see Bonferroni. Let me see. Okay. So that's the only significant thing there if you look at it. In fact, it's only LSD that was almost significant. The relationship, the difference between low dose and high dose. If you look at the other method, it's not even close to 0.0 something. So, and you see the one that is significant also, very significant, the one between low dose and high, placebo and high dose. You see that the LSD is very, very significant, 0.08, while the other one is 0.025, while the other one is 0.039. You know, the smaller the p-value, the more significant. So what does it tell about this method? LSD, Bonferroni, and ANOVA. Bonferroni was the first to make this correction, talk about the correction. Then later, they now say, some people criticize, they say, Bonferroni overcorrected. You know, they corrected for the, what do I call it? The family-wise error. Say, he overcorrected, such a way that sometimes it doesn't make it easily significant when there are differences. That's why if you look at it, the LSD is more loose. You can easily find the difference. One time we were doing the training in Port Harcourt. One PhD student said, okay, that you remember when she was doing her research, he did use Bonferroni and he didn't find different. The supervisor said, go and use LSD. LSD means least square different. Bonferroni is the name of person that describes. Gainsower is the name of the person also. Gain and Howell. So the LSD, we don't know the person, but the method is least square difference. So you can now find where so when the ANOVA tells that there's a significant difference, you can now know that the difference lie in only one place, between the placebo and the high dose. So the logic there is that if you want to use Viagra, use high dose if you want to see any change in the. So low dose Viagra will not make so much change in the libido. But when you use high dose, that makes change, big change. Any question? Any question?
No, sir.
So that's summary of an introduction to analysis of data. It's a very, very interesting method. So all these things are the output is what I put on my slide just to explain. I think it's the same LSD, Bonferroni, and Jim Gabe. So where I use here. So what you can do is just a graph looking at the relationship. Look at it now. If you put this one is not necessary unless we do a regression. It's when we do regression, linear regression, I will still bring this data in to prove. I will not both ANOVA and run regression with it with the dummy I created. It will give you the same thing. The same thing. So if there's no question.